You are listening to Audio SSLC, your audio medium for easy understanding and revision. To download a copy of this recording, please visit audiosslc.com. Chapter 2: Acids, Bases and Salts. You have learned in your previous classes that the taste of sourness and bitterness of the food are due to the acids and bases, respectively, that are present in them. If someone in the family is suffering from a problem of acidity after overeating, which of the following would you suggest as a remedy? Lemon juice, vinegar, or baking soda solution? Which property do you think while choosing the remedy? Surely you must have used your knowledge about the ability of acids and bases to nullify each other's effect. Now recall how we tested sour and bitter substances without tasting them. You already know that the acids are sour in taste and change the color of blue litmus to red, whereas bases are bitter and change the color of the red litmus to blue. Litmus is a natural indicator, and turmeric is another such indicator. Have you ever noticed that a stain of the curry on a white cloth becomes reddish brown when you apply soap or when you scrub soap on it? This is because soap is basic in nature. And again, it turns yellow again when the cloth is washed with plenty of water. You can also use synthetic indicators such as methyl orange and phenolphthalein to test for acids and bases. In this chapter, you're going to be studying the reactions of acids and bases, how acids and bases cancel out each other's effects, and many more interesting things that you use and see in your day-to-day life. Now think about the following question. You have been provided with 3 test tubes. One of them contains distilled water and the other 2 contain an acidic solution and a basic solution respectively. If you are given only red litmus paper, how will you identify the contents of each test tube? Let's come to understanding the chemical properties of acids and bases. We have the acids and bases in the laboratory. Let's go to activity 2.1. You collect the following solutions from the science laboratory, that is hydrochloric acid, HCl, sulfuric acid, H2SO4, nitric acid, HNO3, acetic acid, CH3COOH, sodium hydroxide, that is NaOH, calcium hydroxide, that is Ca of OH2, potassium hydroxide, which is KOH, magnesium hydroxide, which is Mg of OH2, and ammonium hydroxide, which is NH4OH. Now put a drop of each of the above solutions on a watch glass one by one and test with a drop of the indicators that is shown in the table 2.1 of your book. Now what color or what change in color do you observe with the red litmus, blue litmus, phenolphthalein and methyl orange solutions for each of the solutions taken? Then you tabulate your observations in table 2.1. These indicators tell us whether a substance is acidic or basic by change in the color. There are some substances whose odor change in acidic or basic media. These are called olfactory indicators. Let's try out some of these indicators. In activity 2.2, you take some finely chopped onions in a plastic bag along with some strips of clean cloth. Tie up the bag tightly and leave overnight in the fridge. The cloth strips can now be used to test for acids and bases. Take 2 of these cloth strips and check their odor. Keep them on a clean surface and you put a few drops of dilute HCl solution on one strip and a few drops of dilute NaOH, that is sodium hydroxide solution, on the other. Now rinse both the cloth strips with water and again check their odor. Note down your observations. Next, take some dilute vanilla essence and clove oil and check their odor. Take some dilute HCl, that is hydrochloric solution, in one test tube and dilute sodium hydroxide solution in another. Add a few drops of dilute vanilla essence to both the test tubes and shake them well. Check the odor once again and record changes in odor if there are any. Similarly, test the change in the odor of clove oil with dilute HCl and dilute NaOH solutions and record your observations. Which of these, that is vanilla, onion and clove, can be used as olfactory indicators on the basis of your observations? Let's do some more activities to understand the chemical properties of acids and bases. Let's do an activity to see how the acids and bases react with metals. We have activity 2.3. You need to exercise caution, and this activity needs teacher's assistance. Please refer to figure 2.1 in your book and set the apparatus as shown there. Take about 5 milliliter of dilute sulfuric acid in a test tube and add a few pieces of zinc granules to it. What do you observe on the surface of the zinc granules? Pass the gas being evolved through the soap solution. Why are bubbles formed in the soap solution? Take a burning candle near a gas-filled bubble. And what do you observe? You repeat this activity with some more acids like HCl, HNO3 and CH3COOH. Are the observations in all the cases the same or are they different? Note that the metal in all the above reactions displaces the hydrogen atoms from the acids as hydrogen gas and it forms a compound called salt. Thus, the reaction of a metal with an acid can be summarized as acid plus metal giving rise to salt plus hydrogen gas. Can you now write the equations for the reactions that you have observed? In activity 2.4, you place a few pieces of granulated zinc metal in a test tube. Then add 2 milliliter of sodium hydroxide solution and warm the contents of the test tube. Then repeat the rest of the steps as said in activity 2.3 and then record your observations. The reaction that takes place, we can write it down as what follows. 2NaOH, which is in aqueous state, plus Zn, which is in solid state, gives rise to Na2ZnO2, which is in solid state. This is sodium zincate, plus H2, which is in gaseous state. Here again you find that the hydrogen is formed in the reaction. However, such reactions are not possible with all the metals. Let's find out how do metal carbonates and metal hydrogen carbonates react with the acids. Let's go through activity 2.5. You take 2 test tubes and label them as A and B. Then take about 0.5 grams of sodium carbonate, that is Na2CO3, in test tube A and about the same amount, that is 0.5 grams of sodium hydrogen carbonate, which is NaHCO3, in the test tube B. Then add about 2 milliliters of dilute hydrochloric acid to both the test tubes. Now what do you observe? Pass the gas that is produced in each case through the lime water, that is the calcium hydroxide solution, and record your observations. Please refer to figure 2.2 for this in your textbook. The reactions that occur in the above said activity can be written as, in test tube A, we have Na2CO3, which is in the solid state, plus 2HCl, which is in the aqueous state, gives rise to 2NaCl, which is in the aqueous state, plus H2O, which is in the liquid state, plus CO2, which is the gaseous state. In test tube B, we have NaHCO3, which is in the solid state, plus HCl, which is in the aqueous state, giving rise to NaCl, which is in the aqueous state, plus H2O, which is in the liquid state, plus CO2, which is in the gaseous state. And on passing the carbon dioxide gas that is evolved through the lime water, we get the following equation. Ca of OH2, which is in the aqueous state, now this is the lime water, plus CO2, which is the gaseous state, giving rise to CaCO3, which is in the solid state. This is the white precipitate, plus H2O in the liquid state. Then on passing excess carbon dioxide, the following said reaction takes place. CaCO3 in the solid state plus H2O in the liquid state plus CO2 in the gaseous state gives rise to Ca of, in brackets, HCO3, close brackets, again 2 atoms of that. This is in the aqueous state. This is soluble in water. Limestone, chalk and marble, they are all different forms of calcium carbonate. All metal carbonates and hydrogen carbonates react with the acids to give a corresponding salt, carbon dioxide and water. So the reaction can be summarized as metal carbonate or metal hydrogen carbonate plus acid gives rise to salt plus carbon dioxide plus water. Let's get to know as to how the acids and bases react with each other with activity 2.6. Take about 2 milliliters of dilute sodium hydroxide solution in a test tube and add 2 drops of phenolphthalein solution. What do you observe is the color of the solution. Then add dilute HCl solution to the above solution drop by drop. Do you notice any change in color for the reaction mixture? Now, why did the color of phenolphthalein change after the addition of an acid? Next, add few drops of sodium hydroxide to the above mixture. Do you notice if the pink color of phenolphthalein reappear? Why do you think this happened? So in the above said activity, we have observed that the effect of a base is nullified by the acid and the effect of an acid is nullified by a base. The reaction that is taking place can be written down as NaOH in aqueous state plus HCl in aqueous state giving rise to NaCl in aqueous state plus H2O in the liquid state. The reaction between an acid and a base to give salt and water is called as neutralization reaction. In general, we can write down this neutralization reaction as follows. Base plus acid gives rise to salt plus water. Let's move on to the reaction of metallic oxides with acids. In activity 2.7, you take a small amount of copper oxide in a beaker and add dilute hydrochloric acid slowly while you are stirring the mixture. Note down the color of the solution. What do you think has happened to the copper oxide? You're going to notice that the color of the solution becomes blue-green and the copper oxide dissolves. This blue-green color of the solution is because of the formation of copper chloride in the reaction. The general reaction between a metal oxide and an acid can be written as metal oxide plus acid gives rise to salt plus water. Now write down and balance the equation for the above said reaction. Since you know that metallic oxides react with acids to give salt and water, Similar to the reaction of a base with an acid, metallic oxides are said to be basic oxides. Let's move on to the reaction of a non-metallic oxide with base. You understood the reaction between carbon dioxide and calcium hydroxide, that is lime water, in activity 2.5. Now calcium hydroxide, which is a base, reacts with carbon dioxide to produce salt and water. Since this is similar to the reaction between a base and an acid, we can conclude that non-metallic oxides are acidic in nature. Let's go through a few questions and see if you can answer them. Question number 1. Why should curd and sour substances not be kept in brass and copper vessels? Question number 2. Which gas is usually liberated when an acid reacts with a metal? Illustrate with an example. And how will you test for the presence of this gas? Question number 3. Metal compound A reacts with dilute hydrochloric acid to produce effervescence. The gas thus evolved extinguishes a burning candle. Now write down the balanced chemical equation for the reaction if one of the compounds that is formed is calcium chloride. Next, let's see as to what do all the acids and all the bases have in common. In section 2.1 of your book, you have seen that all acids have similar chemical properties. Can you say what leads to this similarity in properties? Again, you saw in activity 2.3 that all the acids generate hydrogen gas when they react with the metals. So hydrogen seems to be common to all the acids. Let's perform an activity to investigate whether all compounds containing hydrogen are acidic. Please refer to figure 2.3 for this activity 2.8. Take solutions of glucose, alcohol, hydrochloric acid, sulfuric acid, etc. Then fix 2 nails on a cork and place this cork in a 100 milliliter beaker. Connect the nails to the 2 terminals of a 6-volt battery through a bulb and a switch. Please refer to the figure for this. Now pour some dilute HCl in the beaker and switch on the current. Repeat again with dilute sulfuric acid. What do you observe? Again, repeat the experiment separately with glucose and alcohol solutions. And what do you observe now? Can you say if the bulb glows in all the cases? The bulb will start glowing in the case of acids, as you can see in figure 2.3. But you're going to observe that the glucose and alcohol solutions do not conduct electricity. Glowing of the bulb indicates that there is a flow of the electric current through the solution. The electric current is carried through the acidic solution by the ions. Acids contain H plus ion as cation, an anion such as Cl minus in HCl, NO3 minus in HNO3, SO4, 2 minus in H2SO4, CH3COO minus in CH3COOH. Since the cation present in the acids is H+, this suggests that acids produce hydrogen ions, that is H+, which is aqueous, in the solution, and these are responsible for their acidic properties. Then repeat the same activity using alkalis such as sodium hydroxide, calcium hydroxide, etc. Then what can you conclude from the results of this activity? Let's find out as to what happens to an acid or a base in a water solution. Do acids produce ions only in aqueous solution? Let us test for this. In activity 2.9, you take about 1 gram solid NaCl in a clean and dry test tube and set up the apparatus as shown in figure 2.4. Next, add some concentrated sulfuric acid to the test tube. What do you observe? Do you find there is a gas coming out of the delivery tube? Now test the gas that is evolved successively with dry and wet blue litmus paper. In which case does the litmus paper change its color? On the basis of the above activity, what can you infer about the acidic character of number 1, dry HCl gas, number 2, HCl solution? This experiment suggests that hydrogen ions in HCl are produced in the presence of water. The separation of H plus ion from HCl molecules cannot occur when water is absent. We can write down the equation as HCl plus H2O giving rise to H3O plus Cl minus. Hydrogen ions cannot exist alone, but they exist after combining with the water molecules. Thus, the hydrogen ions must always be shown as H+. They are in the aqueous state, or hydronium ion, that is H3O+. The reaction can be written as H plus H2O giving rise to H3O+. We have seen that the acids give H3O+ or H+, that is aqueous, ion in water. Let's see what happens when a base is dissolved in the water. The equation can be written as NaOH in the solid state when it is dissolved in water gives rise to Na+, which is in the aqueous state, plus OH- which is in the aqueous state. Then we have KOH in the solid state when dissolved in water gives rise to K plus in aqueous state plus OH minus in the aqueous state. Next we have Mg of OH2, which is in the solid state, when dissolved in water gives rise to Mg2 plus, which is in the aqueous state, plus 2OH minus, which is again in the aqueous state. Bases generate hydroxide, that is OH minus ions in water. The bases which are soluble in water are called alkalis. We've identified that all the acids generate H+, and all the bases generate OH-. We can view the neutralization reaction as follows. Acid plus base gives rise to salt plus water. HX plus MOH gives rise to MX plus HOH. Then H plus OH-, which are both in the aqueous states, gives rise to H2O, which is the liquid. Let us see what is involved when water is mixed with an acid or a base. We have activity 2.10, where you take 10 milliliters of water in a beaker. Next, add few drops of concentrated sulfuric acid to it and swirl the beaker slowly. Then touch the base of the beaker. Do you observe a change in the temperature? Is this an exothermic or endothermic process? When you repeat the above activity with sodium hydroxide pellets, you again record your observations. The process of dissolving an acid or a base in the water is a highly exothermic one. You must take great care while mixing concentrated nitric acid or sulfuric acid with water. The acid must always be added slowly to water with constant stirring. If water is added to a concentrated acid, the heat that is generated may cause the mixture to splash out and cause burns. The glass container may also break due to excessive local heating. Look out for the warning sign as shown in figure 2.5 on the can of concentrated sulfuric acid and on the bottle of sodium hydroxide pellets. When you mix an acid or base with water, it results in the decrease of the concentration of ions per unit volume. that is H3O plus or OH minus ions. Such a process is called dilution, and the acid or the base is said to be diluted. Let's go through few questions. Question number 1. Why do HCl, HNO3, etc. show acidic characters in aqueous solutions, while solutions of compounds like alcohol and glucose do not show acidic character? Question number 2. Why does an aqueous solution of an acid conduct electricity? Question number 3. Why does dry HCl gas not change the color of the dry litmus paper? Question number 4. While diluting an acid, why is it recommended that the acid should be added to water and not water to the acid? Question number 5. How is the concentration of hydronium ions, that is H3O plus, affected when a solution of an acid is diluted? Question 6. How is the concentration of hydroxide ions, that is OH minus, affected when excess base is dissolved in a solution of sodium hydroxide? Let's learn how strong are acid or base solutions. We know how acid-base indicators can be used to distinguish between an acid or a base. We've also learned in the previous section about the dilution and the decrease in concentration of H plus or OH minus ions in solutions. Can we quantitatively find the amount of these ions present in a solution? Can we judge how strong a given acid or a base is? We can do this by making use of a universal indicator, which is a mixture of several indicators. The universal indicator shows different colors at different concentrations of hydrogen ions in a solution. A scale for measuring hydrogen ion concentration in a solution called pH scale has been developed. The P in pH stands for Potenz in German, which means power. On the pH scale, we can measure pH generally from 0, which is very acidic, to 14, which is very alkaline. pH should be thought of simply as a number that indicates the acidic or basic nature of a solution. If higher is the hydronium ion concentration, lower is the pH value. The pH of a neutral solution is 7. The values that are less than 7 on the pH scale represent an acidic solution. And as the pH value increases from 7 to 14, it represents an increase in the OH minus ion concentration in the solution. That is, the increase in the strength of alkali. Refer figure 2.6 for this. Generally, the paper impregnated with the universal indicator is used for measuring the pH.
You are listening to Audio SSLC, your audio medium for easy understanding and revision.
To download a copy of this recording, please visit audiosslc.com. In Activity 2.11, we test the pH values of the solutions that are given in Table 2.2. You record your observations. Find out what's the nature of each substance on the basis of your observations. The strength of acids and bases depend on the number of H plus ions and OH minus ions that are produced. If we take hydrochloric acid and acetic acid of the same concentration, say 1 molar, then these produce different amounts of hydrogen ions. The acids that give rise to more H plus ions are said to be strong acids, and acids that give less H plus ions are said to be weak acids. Can you now say what weak and strong bases are? Let's learn about the importance of pH in everyday life. We find out if the plants and animals are pH sensitive. Our body works within the pH range of 7.0 to 7.8. The living organisms can survive only in a narrow range of the pH change. When the pH of rainwater is less than 5.6, it is called acid rain. And when acid rain flows into the rivers, it lowers the pH of the river water. And the survival of the aquatic life in such rivers becomes difficult. Let's find out as to what is the pH of the soil in your backyard. You know, plants require a specific pH range for their healthy growth. To find out this pH that is required for the healthy growth of a plant, you can collect the soil from various places and check their pH in the manner that is described in Activity 2.12. Also, you can note down which plants are growing in the region from which you have collected the soil. Let's proceed to understanding the Activity 2.12. Take about 2 grams of soil in a test tube and add 5 milliliter of water to it, and shake the contents of the test tube. Then filter the contents and collect the obtained filtrate in a test tube. Check the pH of this filtrate using the help of the universal indicator paper. What can you conclude about the ideal soil pH for the growth of plants in your region? Let's learn about the pH in our digestive system. It's very interesting to note that our stomach produces hydrochloric acid. It helps in the digestion of food without harming the stomach. During indigestion, the stomach produces too much of this acid, and this causes pain and irritation. To get rid of this pain, people use bases called antacids. One such remedy must have been suggested by you at the beginning of this chapter. These antacids neutralize the excess acid, and magnesium hydroxide, also called milk of magnesia, which is a mild base, is often used for this purpose. Let's learn about the pH change as the cause of tooth decay. Now, tooth decay starts when the pH value of the mouth is lower than 5.5. Tooth enamel, which is made up of calcium hydroxyapatite, which is a crystalline form of calcium phosphate, is the hardest substance in the body. It does not dissolve in water, but it gets corroded when the pH in the mouth is below 5.5. The bacteria that are present in the mouth produce acids by degradation of sugar and food particles that remain in the mouth after eating. The best way to prevent this is to clean the mouth after eating the food. Using toothpastes, which are generally basic for cleaning the teeth, can neutralize this excess acid and thus help prevent tooth decay. Let's learn about self-defense by animals and plants through chemical warfare. Have you ever been stung by a honeybee? The bee sting leaves an acid which causes pain and irritation. Using a mild base like baking soda on the stung area gives relief. Stinging hair of nettle leaves inject methanoic acid and it causes burning pain. Please refer to table 2.3 for some naturally occurring acids. Moving on to the questions. Question number 1. You have two solutions A and B. The pH of solution A is 6 and pH of solution B is 8. You have to say as to which solution has more hydrogen ion concentration. Which of this is acidic and which one is basic? Question number 2. What effect does the concentration of H plus ions have on the nature of the solution? Question number 3. Do basic solutions also have H plus ions? If yes, then why are these basic? Question number 4. Under what soil condition do you think a farmer would treat the soil of his fields with quicklime, that is calcium oxide, or slaked lime, which is calcium hydroxide, or chalk, which is calcium carbonate? Let's learn more about the salts. In the previous sections, you have seen how salts are formed during various reactions. Let's now understand more about their preparation, properties, and uses. Coming to the family of salts, we have activity 2.13. You need to write down the chemical formulae of the salts that are going to be mentioned now. They are potassium sulfate, sodium sulfate, calcium sulfate, magnesium sulfate, copper sulfate, sodium chloride, sodium nitrate, sodium carbonate, and ammonium chloride. You need to identify the acids and bases from which all the above said salts may be obtained. The salts that have the same positive or negative radicals are said to belong to a family. For example, NaCl and Na2SO4 belong to the family of sodium salts. Similarly, NaCl and KCl belong to the family of chloride salts. How many families can you identify among the salts that were given in this activity? Let's learn about the pH of salts. In activity 2.14, you need to collect the following salt samples, that is sodium chloride, potassium nitrate, aluminium chloride, zinc sulfate, copper sulfate, sodium acetate, sodium carbonate, and sodium hydrogen carbonate. Also, some other salts available can also be taken. You need to check their solubility in water. For this, you need to use distilled water only. Then check the action of these solutions on the litmus and find their pH using a pH paper. Which of the salts are acidic, basic, or neutral? Also, identify the acid or base that are used to form the salt. You need to report your observations in table 2.4. Salts of a strong acid and a strong base are neutral with a pH value of 7. On the other hand, salts of a strong acid and a weak base are acidic with pH value that is less than 7, and those of a strong base and weak acid are basic in nature with pH value which is more than 7. Let's move on to chemicals from common salt. By now you have learned that the salt formed by the combination of hydrochloric acid and sodium hydroxide solution is called sodium chloride. That is the salt that you use in your food. You must have observed in the above said activity that it's a neutral salt. Seawater contains many salts that are dissolved in it. Sodium chloride is separated from these salts. Deposits of solid salt are also found in several parts of the world. These large crystals are often brown because they have impurities in them. This is called rock salt. Beds of rock salt were formed when seas of bygone ages all dried up. Rock salt is mined like coal. You must have heard about Mahatma Gandhi's Dandi March. Did you know that sodium chloride was such an important symbol in our struggle for freedom? Let's learn about the common salt, which is the raw material for the chemicals. The common salt thus obtained is an important raw material for various materials of daily use such as sodium hydroxide, baking soda, washing soda, bleaching powder, and many more. Let's now see how one substance is used for making all these different substances. Let's see how sodium hydroxide is made from the common salt. When you pass electricity through an aqueous solution of sodium chloride, also called brine, it decomposes to form sodium hydroxide. The process is called chlor-alkali process because of the products that are formed: chlor for chlorine and alkali for sodium hydroxide. We can write the reaction as follows: 2 NaCl, which is aqueous, plus 2 H2O, which is liquid, gives rise to 2 NaOH, which is aqueous, plus Cl2, which is gaseous, plus H2, which is gaseous. The chlorine gas is given off at the anode and hydrogen gas is given off at the cathode. The sodium hydroxide solution is formed near the cathode. The three products that are produced in this process are all useful. Figure 2.8 in your book shows the different uses of these products. Let's learn about the bleaching powder. You have already come to know how chlorine is produced during the electrolysis of aqueous sodium chloride or brine. This chlorine gas is used for the manufacture of bleaching powder. Bleaching powder is produced by the action of chlorine on dry slaked lime, that is Ca of OH2. Bleaching powder is represented as CaOCl2, though the actual composition is quite complex. We have the equation Ca of OH2 plus Cl2 gives rise to CaOCl2 plus H2O. Bleaching powder is used for the following reasons. Number 1, for bleaching cotton and linen in the textile industry. It's used for bleaching wood pulp in paper factories and also used for bleaching washed clothes in the laundry. Number 2, it is used as an oxidizing agent in many chemical industries. And number 3, it's also used to make drinking water free from germs. Next, let's learn how baking soda is made from sodium chloride. The baking soda is commonly used in the kitchen for making tasty, crispy pakoras, etc. Sometimes it is added for faster cooking. The chemical name of the compound is sodium hydrogen carbonate and its formula is NaHCO3. It's produced using sodium chloride as one of the raw materials. The equation is NaCl plus H2O plus CO2 plus NH3 gives rise to NH4Cl, which is ammonium chloride, plus NaHCO3, which is sodium hydrogen carbonate. Did you check the pH of sodium hydrogen carbonate in activity 2.14? Can you correlate why it can be used to neutralize an acid? It's a mild, non-corrosive basic salt. The following said reaction takes place when it's heated during cooking. 2NaHCO3, which is sodium hydrogen carbonate, when heated, gives rise to Na2CO3, which is sodium carbonate, plus H2O plus CO2. Also know that sodium hydrogen carbonate has got various uses in the household. Let's learn about the uses of baking soda. Point number 1. It's used for making baking powder, which is a mixture of baking soda, which is sodium hydrogen carbonate, and a mild edible acid such as tartaric acid. When baking powder is heated or mixed in water, then the following said reaction is going to take place. NaHCO3 plus H plus, that is the hydrogen ion from any acid, gives rise to CO2 plus H2O plus sodium salt of the acid. The carbon dioxide that is produced during the reaction can cause bread or cake to rise, making them soft and spongy. Point number 2. Sodium hydrogen carbonate is also an ingredient in antacids. Being alkaline, its neutralizing capacity neutralizes the excess acid in the stomach and provides relief. Use 3. It's also used in soda acid fire extinguishers. Coming to washing soda, it's another chemical that can be obtained from sodium chloride. Its chemical formula is Na2CO3 dot 10H2O. You have heard from above that sodium carbonate can be obtained by heating baking soda. Recrystallization of sodium carbonate gives washing soda. It is also a basic salt. The equation is Na2CO3, which is sodium carbonate, plus 10H2O gives rise to Na2CO3 dot 10H2O. What does 10H2O signify? Does it make Na2CO3 wet? We will address this question in the next section. Also know that sodium carbonate and sodium hydrogen carbonate are useful chemicals for many industrial processes as well. Let's learn about the uses of washing soda. Number 1. Sodium carbonate or washing soda is used in glass, soap and paper industries. Number 2. It's also used in the manufacture of sodium compounds such as borax. Number 3. Sodium carbonate can be used as a cleaning agent for domestic purposes. Number 4. It is used for removing permanent hardness of water. In the next segment, let's find out if the crystals of salts are really dry. Let's go through activity 2.15 for this, and please refer to figure 2.9 in your book. You heat a few crystals of copper sulfate in a dry boiling tube. What you notice is the color of the copper sulfate after heating. Do you also notice water droplets in the boiling tube? And where have these come from? Now add 2 to 3 drops of water on the sample of copper sulfate that is obtained after heating. What do you observe? Is the blue color of copper sulfate restored? Here, the copper sulfate crystals, which seem to be dry, they contain water of crystallization. When we heat the crystals, this water is removed and the salt turns white. If you moisten the crystals again with water, you're going to find that the blue color of the crystals reappears. Water of crystallization is the fixed number of water molecules that are present in one formula unit of a salt. 5 water molecules are present in one formula unit of copper sulfate. Chemical formula for hydrated copper sulfate is CuSO4.5H2O. Now you'd be able to answer the question whether the molecule of Na2CO3.10H2O is wet. One other salt which possesses water of crystallization is gypsum. It has 2 water molecules as water of crystallization. It has the chemical formula CaSO4.2H2O. Let's look into the use of this salt. Plaster of Paris. When you heat gypsum at 373 Kelvin, it loses the water molecules and becomes calcium sulfate hemihydrate. The chemical formula for which is CaSO4.half H2O. This is called plaster of Paris. It's the substance which doctors use as plaster for supporting fractured bones to put them back into the right position. Plaster of Paris is a white powder, and when you mix it with water, it changes to gypsum once again, giving a hard solid mass. The equation is CaSO4.half H2O plus 1.5 H2O gives rise to CaSO4.2H2O. Here CaSO4.half H2O is nothing but the plaster of Paris, and CaSO4.2H2O, as you know, is the gypsum. You know that only half a water molecule is shown to be attached as the water of crystallization. How can you get half a water molecule? It is written in this form because two formula units of CaSO4 share one molecule of the water. Plaster of Paris is used for making toys, materials for decoration, and for making surfaces smooth. Now try finding out as to why is calcium sulfate hemihydrate called plaster of Paris. Let's move on to the questions. Question number 1. What is common name of the compound CaOCl2? Question 2. Name the substance which on treatment with chlorine yields bleaching powder. Question number 3. Name the sodium compound which is used for softening hard water. Question 4. What will happen if a solution of sodium hydrocarbonate is heated? Give the equation of the reaction that is involved. Question 5. Write an equation to show the reaction between plaster of Paris and water. In the next section, let's look at the things you have learned so far from this chapter. Number 1. You have learned that acid-base indicators are dyes or mixtures of dyes which are used to indicate the presence of acids and bases. Number 2. Acidic nature of a substance is due to the formation of H+ ions in solution. The formation of OH- ions in solution is responsible for the basic nature of a substance. Number 3. When an acid reacts with a metal, hydrogen gas is evolved and a corresponding salt is formed. Number 4. When a base reacts with a metal, along with the evolution of hydrogen gas, a salt is formed which has a negative ion composed of the metal and oxygen. 5. When an acid reacts with a metal carbonate or metal hydrogen carbonate, it gives the corresponding salt, carbon dioxide gas, and water. Number 6. Acidic and basic solutions in water conduct electricity because they produce hydrogen and hydroxide ions respectively. 7. The strength of an acid or an alkali can be tested by using a scale called the pH scale, which is from 0 to 14. It gives the measure of hydrogen ion concentration in a solution. Number 8. A neutral solution has a pH of exactly 7, while an acidic solution has a pH less than 7 and a basic solution has a pH of more than 7. Number 9. Living beings carry out their metabolic activities within an optimal pH range. Number 10. Mixing concentrated acids or bases with water is a highly exothermic process. Number 11. Acids and bases neutralize each other to form corresponding salts and water. Number 12. Water of crystallization is the fixed number of water molecules that are present in one formula unit of a salt. Number 12. Salts have various uses in everyday life and in industries. Let's move on to the exercises to see how much you know. Number 1. A solution turns red litmus blue. Its pH is likely to be A 1, B 4, C 5, or D 10. Number 2. A solution reacts with crushed eggshells to give a gas that turns lime water milky. The solution contains A. NaCl, B. HCl, C. LiCl, or D. KCl. Number 3. 10 milliliter of a solution of NaOH is found to be completely neutralized by 8 milliliters of a given solution of HCl. If we take 20 milliliters of the same solution of NaOH, the amount of HCl solution, that is the same solution as before, required to neutralize it will be A. 4 ml, B. 8 ml, C. 12 ml, or D. 16 ml. 4. Which one of the following types of medicines is used for treating indigestion? A. Antibiotic, B. Analgesic, C. Antacid, or D. Antiseptic. Number 5. Write word equations and then balanced equations for the reaction taking place when A. Dilute sulfuric acid reacts with zinc granules. B. Dilute hydrochloric acid reacts with magnesium ribbon. C. Dilute sulfuric acid reacts with aluminium powder. D. Dilute hydrochloric acid reacts with iron filings. 6. Compounds such as alcohols and glucose also contain hydrogen but are not categorized as acids. You need to describe an activity to prove it. 7. Why does distilled water not conduct electricity, whereas rainwater does? 8. Why do acids not show acidic behavior in the absence of water? 9. 5 solutions A, B, C, D, and E, when tested with universal indicator, showed pH as 4, 1, 11, 7, and 9 respectively. Which solution is A. Neutral, B. Strongly alkaline, C. Strongly acidic, D. Weakly acidic, E. Weakly alkaline. Arrange the pH in increasing order of hydrogen ion concentration. 10. Equal lengths of magnesium ribbons are taken in test tubes A and B. Hydrochloric acid is added to test tube A, while acetic acid is added to test tube B. The amount and concentration taken for both the acids are the same. In which test tube will the fizzing occur more vigorously, and why? 11. Fresh milk has a pH value of 6. How do you think the pH will change as it turns into curd? Explain your answer. 12. A milkman adds a very small amount of baking soda to fresh milk. A. Why does he shift the pH of the fresh milk from 6 to slightly alkaline? B. Why does this milk take a long time to set as curd? 13. Plaster of Paris should be stored in a moisture-proof container. Explain why. 14. What is a neutralization reaction? Give 2 examples. 15. Give 2 important uses of washing soda and baking soda. In the group activity, you need to prepare your own indicator and prepare a soda acid fire extinguisher.